Good evening everyone. I am Chanda Devnath. Good evening everyone. I am Chanda Devnath, one of the PMRF fellows of ISR Barampur. So I am the TA of this course Retrosynthesis in Organic Chemistry, instructed by Professor Shamik Nanda. So here in these classes I usually discuss about some previous year questions based on some reaction mechanisms and name reactions also, which may help you to design a retrosynthesis of any natural products or any compound. So in the previous classes I already have discussed all the name reaction which has been asked to you in your assignments again and again. I have tried to cover up all the name reactions and also some reaction mechanisms and some important reagents also. In this class I am going to discuss some retrosynthesis of some important compounds. Some of the compounds you know about those names, like aspirin, ibuprofen. You have heard the name of this compound. So today I will discuss about the retrosynthesis of such compound. Tomorrow I have another class and that will be our last class. In that class I will discuss about retrosynthesis of some optically active compounds or some chiral compounds, how we can perform a retrosynthesis of a compound selectively so that we can get a specific stereochemistry of the product. Tomorrow I will discuss about such. Today whatever problem we will discuss, that's all are achiral. There is no question of chirality. So let's start. So today's topic is what first we will, in that one slide I will just discuss what is retrosynthesis, and then we will start retrosynthesis of some important molecules. So what is retrosynthesis? Retrosynthesis is a technique which chemists used to identify how to synthesize a molecule through approaching the problem backwards. So if some compound is given, how we can, the retrosynthesis is a process to predict the pathway how that molecule can be synthesized. So this type of retrosynthesis effectively starts from the wanted product and works backward, chopping and changing the molecule into smaller pieces to identify what the previous molecule can be made from. These chopped up molecules are referred to as synthon. Suppose this compound is given.
Hello.
Hello?
It's not audible. Hello.
Hello, I am not audible.
Not audible.
Is this okay now?
Yeah.
Thank you. So I will just repeat once. So today we will discuss about the retrosynthesis, what is retrosynthesis, and some retrosynthesis of some important compounds. Today actually we will mainly discuss about some molecules which are usually achiral. In tomorrow's class we will discuss about some optically active molecule, how we can synthesize those molecules optically in an energy selective way. We will discuss that tomorrow. So today whatever is mainly based on some academic synthesis. So what is retrosynthesis? Retrosynthesis is a technique chemists use to identify how to synthesize a molecule through approaching the problem backwards. So in this case, in case of retrosynthesis, a molecule is given and we will try to solve how that specific molecule can be synthesized from a simple molecule. So this retrosynthesis is effectively start from a wanted product and works backward, chopping and changing the molecule into smaller pieces to identify what the previous molecule can be made from. These chopped molecules are referred as synthon. So suppose this compound is given to you and they have told you to plan the retrosynthesis of such compound. Retrosynthesis of such compound. Now how we can do that? So first there is a double bond is there. So we know alkenes can be formed easily in a reaction where there are multiple types of reaction which I have been discussed also in the previous classes, that how we can form a alkene. So there are multiple reactions by which we can form a alkene. So if you chop this double bond, one of this double bond, what will form? If you chop this double bond, for one chopping of bond, it can give us this. We know some reactions by which we can get this type of compound. Okay, so this type of, after chopping, whatever we are getting, this is synthetic equivalent. Suppose if you are just chopping it, let's change it to different. This compound is given to you. Now as one is this part, another is this one. Now as one bond, if one bond disconnect, then there will be a positive and negative charge. Now here two bonds have been disconnected, so there will be a 2 delta positive or positive charge. There will be 2 positive charge, and as their 2 bonds are disconnected, there will be 2 negative charge. So these are called synthon. Now these synthons are generated from, these are hypothetical. You know that no such compound can exist in this form, like double positive, double negative. So how the compound from which the synthon is generated, that is called synthetic equivalent. Here even thus is called are usually unstable. This can be usually unstable because it's not possible to stay like this with a double positive, double negative charge. Thus, it's important to identify a more stable equivalent molecule which would react in the same way. So these are synthon, but we have to find the equivalent, that is called synthetic equivalent. We have to find the synthetic equivalent of such compound that react in the same way. So the synthetic equivalent of this one, what will be? As there is 2 negative charge, so if we can connect 2 H atom in this position, can connect to each atom at this position. Similar way, as there are two positive charge, you can connect to OH atom. This is also unstable. A geminal diol is also unstable. So the synthetic equivalent of such type of compound will be ketone. Okay. So if you combine these two compounds, you can get this one as our product. So the trick to good retrosynthesis is knowing which bond to break. Like if you just see there are lots of bond, if you instead of this double bond, if you break this one, you will get an idea like how we can get form this compound. Unfortunately, this is something that comes from with practice and experience. If you solve multiple types of questions, if you solve what type of bonds can be formed easily, so you can break that bond first, then in that way. So it comes from the how much you practice this topic. So what is this arrow? The retrosynthetic arrow is used to show retrosynthesis is taking place through breaking a bond, not a reaction. This bond represents, this double bold bond represents that the reaction is going in the reverse way and the bonds are breaking. It's a hypothetical thing, that this is not any such that any reaction is getting performed. That is that we are just hypothesizing that this bond can be break in this way and how this molecule can form from these two primary molecules. So now let's start. First we'll discuss about some retrosynthesis of some known and some important molecules. So this is what everyone knows, this is aspirin. This is aspirin. So we have to predict the retrosynthesis of such compound. How we can perform that? So here it's already shown. If we break this bond, what we will get? We break this bond as a synthon, we will get this O minus and CH3CO plus. Now these are the synthons. These are the synthons. These are the synthons. Now we want to know what are the synthetic equivalent of such compound. So if you just go this way, what will be the synthetic equivalent of such compound? This can be OH and this can be CO2H. And this can be a anhydride. Because This part can act as a good living room. This part can act as a good living room. Okay. This part can act as a good living room. Now, what is the synthetic equivalent of such compound? How this compound, how this salicylic acid can be formed? So if you just disconnect from this part and I'm not drawing the symptoms, I'm directly doing the synthetic equivalent. So if we react a phenol with a carboxylic acid, we'll get this 2-carboxylic acid phenol. Okay, so now everyone can plan the forward synthesis of such compound. What will be the forward synthesis? So this phenol undergoes aromatic electrophilic substitution with carbon dioxide followed by HCl. It will give salicylic acid. After that, if we react this one with this diethyl ester, what will form? It will form our desired product. Okay, target molecule. It will give us our target molecule. Okay, understood? Let's go to the next question. So how will you determine the retrosynthesis of paracetamol? We know paracetamol is the very important medicine for us. So how will you determine, how will you plan, or how this compound is synthesized in company? That we will see. So what will be the retrosynthesis? As I have shown, if you break this bond, what you will get? In the similar way, it will get a NH2 and here you will get a OH, and in the another part you will get a similar type of ester. Now this can be prepared from phenol. If you perform nitration of phenol, you will see it can be this amine can be formed from a nitro, and this nitro can be found from the nitration of phenol. These are all known reactions we have learned again and again. So just retrosynthesis is the application of those reactions. Retrosynthesis are the application of such reaction. Okay, so this will be the retrosynthesis of this compound. So what will be the forward synthesis? As I said, you have to perform the nitration of phenol followed by reduction. This can be performed through TAHip. If you want to know the specific reagent, it can be performed through TAHip. This TAHip will reduce NO2 selectively. TAHip is specifically reduce NO2 group. So this TAHip will reduce NO2 group to NH2. After that, through this acetylation, we will get paracetamol. How will you plan this retrosynthesis of this ibuprofen? I have already shown. How can plan the retrosynthesis of this ibuprofen? Here I have already shown this CO2H can be replaced by CN. This CO2H group can be replaced by CN. In the next step, this CN, this is called FGI, functional group interconversion. In the next step, this a CN group can be replaced with the OH group. Now this OH group can be generated from a ketone. Finally, this compound can be generated. This bond can be broken, and we can get this simple benzene, alkyl benzene, and which can be prepared from simple benzene in this way. So let's see the forward synthesis of this compound. How we can get the forward synthesis of such compound? What will be the reagent? So first, if you perform the fiddle crust acylation, will get of this such compound. If you perform, this can be generated from benzene. This can be okay. So this can be performed from benzene and acyl chloride. This isopropyl chloride, this can be, if you reduce this through zinc amalgam dimension reduction, will get this isobutyl benzene, followed by, if we perform the fiddle cup acylation again, will get this 4. Further, if we reduce this carbonyl group with LiLH4, it will get reduced to alcohol. Then if you perform a substitution reaction by using THCl followed by KCN, THCl, in the next step if you use KCN, this OH group will be replaced by this CN. Again, if you perform acidification, this CN group will be hydrolyzed and we will get acid. The CN group will be hydrolyzed and we will get acid. I hope it's clear. Let's go to our next question. So you have to plan the retrosynthesis of this molecule. Okay, I will just give 10 seconds. Just first, just just think once. I just give 5 seconds. Just think once which bond we have to break first. There are multiple bonds. There is a spiral compound. There is a double bond also. So which bond will be broken first? Just think that. Okay, let's start. So this is a quaternary carbon, and all the carbons. So it's and also alpha beta unsaturated compound. So if we break this bond, how this double bond can be formed? One way is the aldol condensation, another way is Wittig. So if we take the aldol condensation and break this bond, then what will form? If this there will be a positive, double positive charge, and there will be double negative charge, as I have shown. So double negative charge can be replaced by 2H, and double negative positive charge can be replaced by a ketone in this way. So there are 2H has been connected, whereas in this position 2OH which combines to give this carbonyl. Now if you count this is a 1, 2, 3, 4, 5, 6, 5, 1, 6 diketone. So it can form, if we combine from this to this place, it will form a 5-member ring, but if we combine from these two carbonyl, it will give us a 7-member ring. So if we just combine these two carbonyl group, 1, 2, 3, 4, 5, 6, if we just combine these two carbonyl group, what we will get? This alkene. We get this alkene, because we know that whenever the alkene is performed through ozonolysis, these two alkene will flip and we will get 2 carbonyl. So if we do that way, so if we combine these 2 carbonyl, we will get this alkene. Now we know that alkene is a good product, or the source of alkene is through elimination. The alkene can be generated from elimination. Alkene can be generated from elimination. So if we try to perform a E2 elimination type of reaction, now there are 2 possibilities. One is leaving group. If we place the leaving group here and another plus an H here, and another possibility is reverse. Now if we place the leaving group in this place, suppose if you place the leaving group in this place, what will happen? There are 2 H are available. One, so to generate double bond selectively to this place, you have to, but if you place the leaving group in this middle portion, there is also 50-50 chances where the double bond can be formed at this place through elimination of this H. So to get selectively this double bond, we have to place the leaving group at this position. So we have to place the leaving group at the terminal position, not in the middle position, so that this OH will be eliminated selectively to give us this double bond. Okay, so we have to place a leaving group. OTS is a good leaving group. We have to place a leaving group at this position. In this case, this H will selectively remove and give us this alkene. Now if we replace this OTS with a OH, it's possible that replace the OTS with a OH because tosyl protection can be performed. Now this OH can be formed through reduction of a ketone, so it can be replaced with a ketone. Now we know the alpha position of a ketone. The alpha position of a ketone are highly nucleophilic because of enol formation. So this part can be, if you break this bond and then there will be a positive charge and there will be a negative charge. So if you get this from a phenyl benzyl bromide, or if this negative charge can be formed through a enol formation. So you can get through breaking this bond, if you will get this one along with benzyl bromide. This can be performed through enolate chemistry. This can be formed through enol formation. Now this you have synthesized this compound in your previous year questions when you solve the questions of E1 elimination or pinacol-pinacolon rearrangement. You have seen this compound when you synthesize pinacol-pinacolon rearrangement. So this can be formed through a pinacol-pinacolon rearrangement. If we start from these two compounds, we start from this compound. Through pinacol-pinacolon rearrangement, it will give us this compound, because this OH will be eliminated, then the double bond, this ring bond shift, and then neutralization. Again, this diol can be synthesized from cyclopentanone. This diol can be synthesized from cyclopentanone. So what will be the forward synthesis of this compound? We'll start from cyclopentanone, 2 molecules of cyclopentanone in presence of magnesium. It will, through radical pathway, give a radical, an O radical, which will combine with magnesium. Magnesium will give one radical to one molecule and another radical to another molecule. So it will give us this compound where C is joined to magnesium plus 2 another molecule. It will undergo the radical coupling. It will undergo the radical coupling, and under acidification, if we add H plus, this OH will be acidified to give us this diol compound. Now if you add H plus, it will undergo the pinacol-pinacolon rearrangement, giving this compound. Now if you add LDA, then this proton will be eliminated and form a enolate followed by a benzyl bromide. This will be incorporated at the alpha position. Okay. Further, if you reduce this carbonyl with LiLH4, and in the next step, if you protect it with the undergoes a tosylation with the THCl, it will form this OTS. The next, if you perform elimination by using NaOH, as base. There will be a generation of double bond. At this place. Now features perform ozonolysis across this bond, where this bond will break and form a ketone. Will form a ketone. Now after that so you have to perform now if you perform aldol concentration of this aldehyde, because if you undergoes aldol condensation, obviously the aldehyde will react first. So if you aldol condensation, then this aldehyde will react and there are alpha each at this position, and you will get this 5-member ring with a double bond and a spiro with another 5-member ring and also a ketone adjacent to that. Okay, so this will be the forward synthesis of this target molecule. Okay, let's go to next question. So what will be the retrosynthesis of these molecules? These are very simple. So as we have learned, whenever there is a double bond, we have to break that double bond. We will break this double bond, and what we will get? We will get a ketone, and if you add 2H, then there will be a CH3. So this can be formed easily through aldol condensation. So this can be formed easily through aldol condensation. So the forward synthesis will be, if you add any base, then this alpha position, this will be enolate formation. It will attack to this ketone. It will be OH. After that, through elimination, you will get our desired product. Now what will be the retrosynthesis of this compound? What will be the retrosynthesis of such compound? So it can be formed if you break this bond. This is a ester bonds can be easily broken and formed. So what will if it will form a ester, and there will be a OH. Okay, it will be ester and a OH. Now in the next step, as this is a 1, 2, 3, 4, so it can be formed through 1/4 addition. So if you plan, if you just break this bond and then imagine there is a negative charge at this position and a positive charge. First it can be transformed to a ketone, then there will be a positive charge at this position. So these are the synthon. What will be the synthetic equivalent of this one? It can be formed to a diethyl oxalate, and this is the alpha beta unsaturated ketone. These are the synthetic equivalent of this synthon. So what will be the forward synthesis of this compound? This will be the forward synthesis where this alpha beta unsaturated compound react with this nucleophile to form this compound. Then through reduction, this will reduce this ketone selectively. After that, this ketone will transform to OH and react one of the CO2 group. In the next step, if you perform H plus and heat, this CO2 group will be carboxylate and will transform to a carboxylic acid, and due to heating it will be decarboxylated to form this target molecule. This will be eliminated as a carbon dioxide. This group will be carboxylate, hydrolyzed and eliminated as a carbon dioxide. So this is the forward synthesis of such small molecule. So now you can try this way, you can predict any forward synthesis of any compound. Now the thing is, they have given this forward synthesis, you have to predict the reagent for this forward synthesis. So let's start. First they have given this Grignard and from that they have formed this product. Now suppose this part is here. So if you just break this bond, what will happen? If there will be a negative charge and positive, negative charge can be equivalent to this Grignard because there is a delta negative charge. So there will be a positive charge. Now there is already a OH. If there is one positive charge, you can replace that positive charge with another OH. Now two OH means that will be replaced by a ketone. So it can react with a ketone. Because 2 OH means that's a ketone. Understood, right? If you break this bond, there will be a delta positive and there will be a delta negative. Now delta negative can be replaced by this Grignard. Now delta positive can be equivalent to 1 OH. Now if we place 1 OH here, 2 OH, geminal OH, it means it is a ketone. Now in the next step, what happens? There is a aldehyde. So how it is possible? If you just deprotect this, deprotect this part, you will get an aldehyde. In the next step, if you perform a Wittig type of reaction with this CHO, you can generate this double bond. Let's see the reagents. As I said, that if you just deprotect this part, you will get a CHO. Now see, and under the same reagent condition, this OH will be eliminated and give us this alkene. Now in this compound, see, there is no alkene, so we have to reduce this double bond. In presence of H2 palladium charcoal, it selectively reduce the carbon-carbon double bond, so it will be reduced. In the next step, if you react with this aldehyde with the Wittig, we can get a specific Wittig. We can get this double bond. This is, if you react with this specific Wittig, we will get this double bond. Okay, so by this way you can predict the forward synthesis of this compound. Let's go to our next question. So you have to predict the forward synthesis of this compound. So whenever there is a triple bond, just try to break the single bond adjacent to that, because we know sp carbons are highly electronegative, so these carbons can take a negative charge. So if you break this double bond, what will happen? There will be a delta positive charge. There will be generating a positive charge, and there will be a negative charge. So the positive charge can be replaced through a leaving group, and the negative charge can be replaced by a H atom. So if you add a base and take up this proton and generate a negative charge, and that can attack to this electrophilic center, we will get our target molecule. So this will be the forward synthesis, where you add a strong base that will take a proton from this position and generate a negative charge here, and this negative charge will attack to this alkyl group. This part, it will attack to this part and give us our desired product. Okay, now let's try to get the retrosynthesis of this compound. See, this is a symmetric compound. In the both sides they are symmetric. So both the part are coming from the same compound, that you can get an idea, because both sides are symmetric. So if you break these two bonds, what will happen? Both are same. So if you consider this as a negative charge synthon, 2 molecule of this one and as 2 molecule of this one, so that means there will be 2 positive charge. Okay, so how is this possible? Now this one molecule of negative charge can be generated at the carbon position, that can be formed through Grignard. And this one positive charge can be replaced by which another positive charge can also be replaced by I star. This can be generated from star compound. Okay. So what will be the forward synthesis of this compound? This one. So what will, if you take this bromo compound and undergoes this Grignard formation. It will form a Grignard MgBr, and that will react with MeCO2. First molecule of MeCO2 will replace the OET. Another molecule of CO2 will open up the CO bond and give us this as our desired product. The first molecule of CO2, the Grignard will attack here and replace the OET, and another molecule of will attack here and open this CO bond. Okay, this is the first molecule of, and this is second molecule. Understood, right? It was easy. Now we can perform the retrosynthesis of, if any compound is given to you, you can perform the retrosynthesis. Now the problem is, when suppose any compound has a chiral center, so you have to perform the reaction in an enantioselective manner. So how we can perform a reaction in an enantioselective manner, that we will discuss tomorrow. Okay, so for today's class we have discussed about synthesis of these achiral molecules. So this is homework for you. Multiple steps question which will help you to get an idea how to predict the retrosynthesis of any compound. So you have to plan the retrosynthesis of this compound from this one. How will you get this compound from? We have to plan the retrosynthesis to get this compound from this substrate. So here everything is written, just the OH has been eliminated. The first option is given that, so just try to solve according to one by one. So in the first one, what will happen? This will be a ester, thioester, and there is a below H. It will be eliminated and create a double bond here. And through BU3SNH, this double bond can be reduced. Next is I2PPH3 imidazole. It will also create a double bond here, but here they have added H2PD. So its H2PD can reduce this double bond also. This H2PD can reduce this double bond also. Because of that, so let's start. First, just for A, there will be a 6 member. Now, this reagent we have discussed earlier also. This is a reagent of Chugev reaction. So what will happen? It will form a thioester. will form a thyristor. Now we know there is a scene H is available. But you have to notice that it will form up to this, but you have to notice in the second step I have told already, in case of Chugaev reaction you have to heat the substrate at a very high temperature, like greater than equal to 400 degrees centigrade. So in the second step they have not mentioned about the heat, so it will not undergo Chugaev type of reaction, whereas before it can go to a Chugaev type of reaction, the next reaction will take place in the reaction. So that is SN. This is it. So we know that BU3SNH and AIBA generate BU3SN dot BU3SN dot. See this SN dot this SN dot will add up to this sulfur. This goes here and this bond breaks. See, I have shown in a single headed arrow because the dot is reacting, a radical is reacting, so you have to show through a single headed arrow. I am not writing the OBN. Okay. So there will be a radical generated. Now this radical will take proton from BU3SN, another molecule of BU3SNH. We get our desired product. Let's try the another. So in the first one that we are getting the product, let's try the second B for get just to be sure. So why not B? See, there by seeing the second reaction you can eliminate that they have added H2PD. So we know that H2PD are prone to reduce the double bond, which is less electron rich. So between these two, if there is double bond here, now as there is a double bond already in this place, so it is prone to reduce this double bond also, but here in the product the double bond was intact, so B will be not our desired process. In this one, so this OH will be silicon the correct option will be option A. Tomorrow I will try to solve this question. Before that, just take a look and try by yourself what will be the retrosynthesis of this compound. I'll solve this tomorrow. Okay, so thank you everyone. Thank you for attending my class. I will see you in the next class tomorrow at the from 4 to 6. So this is the recap of today's class. Today we have discussed about what is retrosynthesis. Then we have synthesized the retrosynthesis. We planned the retrosynthesis of aspirin, paracetamol, ibuprofen, then this molecule, this pyro molecule. Then we plan the retrosynthesis of these simple molecules, simple small molecules. And we have also planned get an idea about the reagents for synthesizing these biologically natural products. Next, we have also designed the retrosynthesis of these small molecules. So thank you everyone. We'll meet you in the next class. Have a nice day.